Our next speaker is Professor John Matter from Princeton University, and he's going to talk about Arnold diffusion in 2 1/2 and 3 degrees of freedom.
Thank you. So I guess I first heard of Maurício Peixoto in 1961, I think it was, when I was a sophomore at Harvard. Shlomo Sternberg was extremely enthusiastic about a result Maurício had just gotten, which is structural stability of vector fields on surfaces, the generic structural stability. So that was when I first heard of him. And I guess I first met him when I was a graduate student at Princeton. He visited Princeton, and we talked a bit. And so I was very pleased to meet him. And people here have kindly invited me many times. So I guess the first time was in 1971 in a conference in Bahia, and then I visited IMPA, which was at that time in downtown Rio, a very small building. And I've come back many times. It's been very pleasant here, and I'm very pleased to be back. I guess it's quite a while since I've been back last time. Now, I want to talk about a result I announced at a conference in Russia in 2002, and I've been writing it up ever since. And actually, I think that the way to talk about it is not start in 2002, but start in 1980. So I'll talk about everything I've done in the past 30 years in 45 minutes. I'm going to skip a few details. Okay, so actually it started almost by accident. I just noticed, I heard a talk by Percival, and a rather puzzling talk, and I connected this something I'd read by G.D. Berkoff, which was a very elementary exposition. And I came up with sort of a kind of very soft generalization of KM theory for a very special case. This is for twist maps on a cylinder. So I have a cylinder, and I have a map, the cylinder. And the twist map condition is that it takes the vertical and it always turns in one direction as you go around. So this is and then I assume it's area preserving. Actually, I assume it's exact area preserving. I won't stop to say what that is. So for this situation, well, you can start with an example where the whole cylinder is filled with invariant circles. I mean, each circle as you go up is preserved, and then you can perturb that slightly. And Moser proved that if you make a small enough perturbation in the original paper, I think it was in C333 topology, that there are lots of invariant curves. And Percival in his talk had a new type of Lagrangian I'd never seen before. I guess he invented it. And I noticed that if you combine that with some observation in Berkoff's paper, that you could actually prove not only that there were, he proved that the invariant curves could persist when certain invariant curves persist. So when you have if you have an invariant curve with a rational rotation number, it doesn't persist. It breaks up. That was already proved by Poincaré in ancient times. And he proved that if you have an invariant curve which satisfies Diophantine condition, which means that it's not too closely approximated by rational numbers, then it persists. And what I noticed was that even when you don't have an invariant curve, so for this rather global condition, even when you don't have an invariant curve, you have something which is very much like an invariant curve, which is called an invariant Danjois minimal set. So there's this invariant Danjois minimal set. Actually, for every irrational rotation number, there's an invariant Danjois minimal set. And And then, well, okay, this is 1981. Now I'll skip forward to 1991. And I should mention also that this was also approved in a paper, actually appeared a year later by Aubry and Le Daron. In fact, later Aubry showed me that he had lots of preprints, physics preprints. Well, he wasn't talking about area-preserving mappings per se, but he was talking about a problem in solid-state physics, which, if you like, can be reformulated in terms of area-preserving mappings. I won't say what the problem in solid-state physics is. This take me too much out of my way, but mathematically, the two things are the same, even though physically they're completely different. So he had actually observed these invariant Danjois minimal sets in some sort of, well, he gives some sort of argument for it, which is very physical and not mathematically rigorous. But then the paper of Aubry and Le Daron gave it mathematically rigorous proofs. Actually, what they did went somewhat beyond what I did. Okay, so now let me go ahead a little bit. Actually, let me go back. So in ancient times, Birkhoff proved that if you have a sort of an obstruction from an orbit going from bottom to top, then it's actually an invariant curve. I mean, you might imagine you have an obstruction which is an invariant pseudocurve or something like that, something really wild, but it isn't. What he proved was that it's actually an invariant curve, and it's a graph of a Lipschitz mapping from the base to the other thing. So you have, and from his theorem, you can easily prove that the set of invariant curves forms the closed set because there's an a priori bound on the Lipschitz constant of the curves. So you look at, you can take one of these twisted free-morphisms, take the set of all invariant curves, it's a closed set, and the complement, each component of the complement is an annulus. And another theorem Birkhoff proved was that you could have, if you take an arbitrarily small neighborhood at the bottom of the annulus, arbitrarily small neighborhood at the top of the annulus, there are orbits which go from near the bottom to near the top. Anyway, this interested me, and I somewhat improved Birkhoff's result. So you have, by my result and by, well, also Aubry's result, in between these two invariant curves, you have, they have different rotation numbers, but for every rotation number, between those rotation numbers, there's an invariant Danjois set, now it's called Aubry-Mather set, which is a Cantor set. Actually, for the discussion I have here, you see, I proved the existence of a Cantor set. Actually, Aubry proved a little more. He discussed some sort of minimizing principle and showed that the minimizing principle defines an invariant set which contains a unique minimal set. The unique minimal set is a Cantor set, but there may be other points in the set. Occasionally there are. I mean, if you're familiar with Danjois' theory, this should be very familiar, because in Danjois' theory, if you have a homeomorphism of the circle, there's a unique minimal set. And this is sort of the same sort of thing. So there's this set I found, and a slightly larger set, sometimes slightly larger set that Aubry found. Most of the time, generically, they're the same. But sometimes they're slightly larger. Anyway, as long as the set that Aubry found is not a circle, there is no invariant circle. And by Birkhoff's theorem, you have orbits going from bottom to top. And so my improvement was, if you take two of these sets in this region, you can find an orbit which backward time converges to one of them and forward time converges to the other. Well, that's one problem that people study in dynamics, is try to find orbits which go from one place to another. So this is an example of a success in finding orbits which go from one place to another. And I got very enthusiastic about this idea, and I wanted to study this in more degrees of freedom. There's a well-known question in more degrees of freedom that sort of comes from looking for converse of Kolmogorov-Arnold-Moser theory. So let me discuss this. Usually people discuss this in terms of autonomous systems, but for my discussion it's a little easier to discuss it in terms of time periodic systems. So I want to consider a Lagrangian system. So if I have a Lagrangian system, I want to have it of the form L theta theta dot t. So theta is theta 1 up through theta n is contained in the n torus. And theta dot equals theta 1 dot theta n dot. So these are velocities. Is contained some n ball contained in Rn. So say smooth manifold, smooth convex set with smooth boundary with non-empty interior and smooth boundary. And now, well, in KM theory, one discusses a Lagrangian, which is a perturbation of an integrable Lagrangian, plus, well, usually one does it in Hamiltonian formulation, but it's equivalent to do a Lagrangian formulation. And for my methods of proof, the Lagrangian formulation is much better. So I'll do everything in Lagrangian formulation. So you have a system of this form. So here's the integrable system. And the solutions will satisfy, if you write down the Euler-Lagrange equation, well, okay, I'll write it very quickly. dl dt was it dl theta dot dt equals L theta is the Euler-Lagrange equation. If you here L theta, derivative of L with respect to theta is 0. So in that case, you just have dl theta dot dt equals 0. And in fact, what I want to suppose that L0, that the Hessian matrix of the Hessian matrix of second derivatives of L0 is positive. That is positive definite. So this is, in fact, this is a rather strong assumption, stronger than it's usually assumed in KM theory, where in KM theory one just assumes that it's that this matrix is non-degenerate. But for what I want to do is I want to assume that it's positive definite. And now so by KM theory now, this is a way of writing a small perturbation of an integrable system. Here you have the integrable system, and here you have a small perturbation. So let me assume. Well, of course, this is kind of superfluous to write epsilon times p, because anything I put here can be written as, I can put any epsilon in and write epsilon times p. But so I put some condition on p, maybe p to C4 derivative of p equals 1 or something like that. Then epsilon and p are uniquely defined. So I'll write a small perturbation of an integrable system, and well, if this is CR with enough derivatives, I've forgotten now. Michel Herman got the derivatives down to a minimum. I think it was n plus 1, or no, 2n plus 1. Anyway, r greater than something. 2n plus 1 maybe. Then the system has lots of invariant. The original system, for the original system, when I assume this condition, this comes down to theta dot equals constant. So it has a very simple form. And of course, d theta dt equals theta dot. And now I'm taking theta in the torus, and I'm taking theta dot in Rn. So the whole thing is a torus dot Rn. It's just like this picture. Here I have a circle across R, but now I have a torus like Rn. And the unperturbed integrable system simply takes each of these tori and rotates it by differing amounts. Here, the rotation vector is in Rn, but it's the same sort of picture as you have here. And then when you perturb the system slightly, what the KEM theory says is that most of the invariant tori survive. Now, actually, so I said I wanted to take a time-dependent system, and I want it to be periodic. So this is the sort of system I want to describe. I only choose this system because it's easier to describe my results in terms of this system rather than in terms of an autonomous system. Okay, so. Yeah, the original system is time independent. The original integrable system. Yeah, but that's no real restriction, because if you have an integrable system which is time dependent, you can reduce it to one which is time independent. But okay, so you have to mix time with the other variables. Anyway, it's okay. So but this is the sort of system I want to describe, So now, these tori, well, let's see, if you're, I said that this is an n-dimensional space. So I have n, the tori are 2n plus 1. So I have really a phase space whose dimension is 2n plus 1. So I have the phase space so there's a time factor in here. So there's what's called the angular variables and the action variables, and then there's a time factor. So the dimension equals 2n plus 1. And the dimension of the invariant tori equals n plus 1. So now, if you take n equals 1, you have 3, and here you have 2, and the invariant tori separate the phase space into two. If you have an invariant torus, it separates the phase space into two components. So if you have two invariant tori, well, you have a picture just like I have here, where there's the region between the two invariant circles, which contains no invariant circles, called a Birkhoff region of instability, and you have the same picture. That's for n equals 1. Now, for n equals 2, the
the phase space has dimension 5, and the invariant torus has dimension 3, and you have that the invariant torus separates the does not separate the phase space, and so this leads to the conjecture that the orbits wander all over phase space. There's nothing obvious to prevent them from wandering over phase space. So this notion, this idea that they wander all over phase space, well, there's something called Arnold diffusion. Arnold made a very specific conjecture, and he also gave some examples where his conjecture was satisfied. But I think I'm not going to explain his conjecture. But his conjecture is for arbitrary n. So with my methods, I haven't succeeded in saying much for arbitrary n, but I can say something for n equals 2. This is the first case. I want to say. So let me say what I think I can prove after I write 500 pages or something. So I take, I had my phase space, which is Tn cross Bn cross T. Now I want to focus on this factor. So what I take is, I take sets, let me take a set B epsilon n equals the points of distance greater than epsilon from the boundary. So it's fix some epsilon greater than 0 and take those points. And now I take U1 up through UN contained in B epsilon n. And so these are open sets. And so what I can prove is that for generic small perturbation, so given open sets, given U1 up through UN, they can be arbitrarily small. Open, well, they have to be non-empty. And now I'd like to construct an orbit which goes through these different sets in some order. In fact,
you're using n for different senses, right?
Yeah, you're right. K, okay. Call this K. Actually, this n is now 2, so yeah, okay, but I'll call it K. Okay, so I can find an orbit which goes through each of these. In fact, if you give me an order in which I want to go through them, say in infinite order, I can find an orbit which goes through them in infinite order. And the method's based on some sort of minimization of the Lagrangian. Well, I mentioned, let me draw this picture again. I mentioned that you have this Birkhoff region of instability, and then in between you have all these Dangerois minimal sets, which are minimal also in a completely different sense. I mean, when you say Dangerois minimal sets, because it's minimal in the sense of topological dynamics, but these are also obtained by minimizing appropriate Lagrangian. In my original paper, I minimized, well, I had the opposite sign, so I maximized Percival's Lagrangian, but physicists prefer to minimize, so I changed my sign, and now I minimize it. Yeah, actually, one interesting point here is that you can prove that the Lagrangian has a maximum as well as a minimum, but the minimum corresponds to orbits and the maximum does not correspond to any orbits. So this is somewhat different from the usual calculus of variations. Anyway, so there's this set obtained by minimizing something, and in my version it was Percival's Lagrangian, and in Aubry-Ladron method it was some sort of action, which well, Percival's Lagrangian was also an action, but it's a sort of different kind of action. I mean, action is always given by the same formula, but see, if you're a physicist, all you care about is the formula, so action's always the same. But if you're a mathematician and trying to prove existence theorems, then you have to have it defined on some space. So the difference is what space we define it on. But I can't give any details on that. But I see. I constructed these orbits which go from one point to another by using constrained minima. Well, by the time I constructed these orbits, actually this is 10 years later. It's 1991, so I was thoroughly familiar with Aubry's methods, Aubry-Ladron's methods by then, and so I used their type of space, but I mean, as I said, the actions can be defined in different spaces. So, but a considerable modification of it, which is I look for some kind of constrained minima. See, the orbits correspond to well, in Aubry-Ladron method, they correspond to. I start using their terminology. They were talking about solid state physics, and they weren't talking about invariant curves of mappings. They were talking about crystals, and crystals made of atoms. So there are a bunch of atoms, and you minimize some energy functional, which is the same as the action, and so you can find atoms which satisfy the minimizing principle. And what I did was I found a way to, instead of minimizing, what I do is I put some constraints on the atoms. So I say that the atoms have to be here or here or here. They're constrained to lie in open sets. And then I minimize with the constraints. And as long as the minimization with the constraints actually lies in the open set, doesn't go to the boundary, it corresponds to an orbit. Well, sort of if you choose the open sets at random, you get something which will go to the boundary and you're lost. But if you put a whole bunch of conditions on the open sets, basically coming from the fact that they're very near, for a long time it follows one of these orbits you already know exists, then you can show that the atoms you get are inside the open set, and you actually get an orbit. So you can the basic strategy of the proof is to put the constraints first. You have these two Aubry sets. You first put the constraints so that this is corresponding to the bottom Aubry set, then you gradually increase the rotation number. So you have a variety of constraints. For finite interval you have the bottom one, and then for another finite interval you have one slightly higher. And if you can show that if you make the change sufficiently slow, you can get an orbit which goes from one Aubry set to another Aubry set. In fact, you can get it from going from the bottom to the top, like Birkhoff did. In fact, then you can also make it from going from the bottom to the top, or from one Aubry set to another, and so on, and sort of arbitrarily. And a very important property of these sets for this argument is that they're zero-dimensional. Anyway, so I wanted to generalize this, and this result I just mentioned is my generalization, and it's the basic strategy of the proof is the same, but you need to, but things become vastly more complicated, unfortunately. So, how much time do I have left? 20 minutes? Okay. So the idea is I want to, so I have a, so now Bn is now B2. So I'm in 2 dimensions. So this is the only case I've been able to treat so far. So I want to go, I take a line, so the intuitive idea is I take a line, I take a resonant line in B2 epsilon or something. So resonant means that, well, B2 epsilon is contained in actually line segment. B2 epsilon is contained in R2. And so it's the set of omega 1, omega 2, which satisfies a condition like K1, omega 1 plus K2, omega 2 plus K0 equals 0, where K1, K2, K0 are all contained in Z. And I might as well take them so that the greatest common divisor is 1. And I take K1, K2 not equal to 0. So that defines a resonant line. And now, basically, I use the same strategy that I used here in this case. And I'd say there's 2 steps in the strategy. Step one is describe the location of the Aubry sets. And step 2 is describe, use this information to prove the theorem. Now, this turns out to be very complicated. So both parts are very complicated. Actually, in the meantime, actually, there's a paper of Sheng and Yan who consider a related question. They consider a situation where you have one rotator and as many pendula as you like. That describes a dynamical system. And then you perturb it slightly, and they prove a version of what I proved in that situation. In that situation, in fact, they also have step 1 and step 2. And I think I could use their method in step 2 which is actually not very different from the method I described in my announcement for step 2. I could use their method to prove step 2 in my version. I think maybe theirs is a little more flexible and easier to use. But so in some sense, step 2 has already been carried out, which is, I suppose, nice because I haven't written a word about step 2 so far. I've written about 260 pages involving step 1. The reason it's so long is that Well, it's kind of I say describe the location of the Aubry sets. Well, it's a very nice geometry. I mean, it has all sorts of hills and rivers and whatever you call them. I mean, the geometry is very complicated and very interesting. So it's lots of fun, but since it's so complicated, for all the different geographical features, I have to have a different proof for every one of them, and it just goes on and on. So I guess I should say something about the location of the Aubry sets. See, as I said over here, the key factor is that the Aubry sets are all zero-dimensional. I mentioned before, that I showed the existence of invariant Cantor sets, which are called Donjuan minimal sets, and Aubry-Ledron discussed a certain minimizing principle, and they get certain sets. Well, they're crystals in their version, but they correspond to invariant sets for the mapping, and the invariant sets that they get have unique minimal sets in the sense of topological dynamics, which are my sets. So their sets are a little different from my sets, but they're very similar. Their sets are these Cantor sets with maybe some points in the complementary intervals. But in the discussion of this proof, it's their sets which play the essential role, even though they aren't very different from my sets. The difference is kind of crucial in the proof. So this is why I say describe the location of the Aubry sets, which, there's some notion of Aubry sets which generalize their sets. I define this notion of Aubry sets in more degrees of freedom. I think it's, I can't describe it in a few words, so I think I'll just skip that. But they're defined by an action minimizing principle, and once you define something by an action minimizing principle, it's possible to prove the existence of other orbits by a procedure something like what I did here, where the idea would be the direct generalization would be to use constrained minima, just as I did there, but that didn't seem to work too well. So I found another method, which I called method of changing Lagrangians, which is quite similar to the changing the constraints, but it takes care of certain difficulties which come up when you try to generalize it in the obvious way. Okay, so I want to say something about the location of the Aubry sets. So I have this line. Let me draw the line again. Gamma. And I want to move along gamma. Actually, to get this result, I'll take several lines and move along the different lines in turn. But the main part of the proof is moving along one line. It turns out that with my method of proof, I don't think there's a great difficulty in turning the corner here. I should mention that a great deal of work has been done also by other people. There's a team, Joliava's one of them, and I think he's sort of the inspiration. I don't know who gives the proofs, but let's see, Sarah, and I'm sorry, I don't remember another name. And anyway, they have somewhat similar results, but by different methods, completely different methods. These methods are variational, and their methods are use KM theory and stable and unstable manifolds and intersection of stable and unstable manifolds. And I can skip all that, but then if you look at the sets involved in my discussion, many of the sets are the same as the sets that, in their discussion. It just happens, well, I gave a different definition. But also I have some other sets that they don't have with an action minimizing principle. So there are a lot of similarities between the two proofs, but there are a lot of differences too. So I start with this, I keep drawing this line, gamma. And then I have, I can take DL0. So DL0 maps Bn into Rn. I mean, L0 is a mapping from Bn to R. So if I take its derivative, it's a mapping of Bn into Rn. And so this line goes to some curve. And what I want to do is how much time do I have now? 10 minutes? Okay, so what I want to do is describe the Aubry sets. Now, it turns out that associated to the Lagrangian L, there's a function which is beta L. So I'm waving my hands a lot. So beta L is equals the average. Well, so if I have a homology class containing H1 of T2 with coefficients in R, so T2 is the state space. Then there's a quantity associated to it, beta LH. So I said these Aubry sets are defined by a certain action minimizing principle, and there's an average action associated to it. So this is some sense you can think of this as the average action of an Aubry set with rotation number H, to be very sloppy. So this is average action. And then there's this actually turns out to be a convex function. So beta L from H1 of T2 with coefficients in R to R is convex, or superlinear growth. And now, so you have this theory of Fenchel. Given a convex function on a finite dimensional vector space, there's a dual function, alpha L, which is the Fenchel dual, mapping H1 of T2 coefficients in R into R. And then there's given a convex function, there's you have the Fenchel, there's what's called the Fenchel inequality, which in this case, this is absolutely general, but in this case it comes down to beta LH plus alpha LC is greater than or equal to HC. Okay, so here H is a homology class, C is a cohomology class, and this is the dual pairing. So this is just from Fenchel's theory, which is actually quite, I mean, his paper was 5 pages long, and so he got all these things in 5 pages. Not very, very hard once you see it, but it's very fundamental to a lot of things. And and then there's the Fenchel inequality, Fenchel equality. Which you just replace this with equals. So this holds all the time, and this holds sometimes. You can be more precise that given an H, there's a C for which this holds, and given a C, there's an H for which this holds. And given an H, the set of C for which this holds is a compact, convex, non-empty set. So I was trying to draw this picture here. And now if you do the Fenchel-Lagrange transformation, well, I thought at one time I had a nice, the image of this curve. See, the image of a point is no longer a point. I mean, the derivative is if you take the derivative, given a point here, you get a point here. But given the Fenchel-Legendre transform, so I didn't say what the Fenchel-Legendre transform was, but given H, there's the set of C satisfying this is non-empty, compact, and convex. So that set is called the Fenchel-Legendre transform of H. And actually, for most of these things, the Fenchel-Legendre transform is a line, which in the union of these lines, most of the time it contains DL0, and but sometimes if you're near a strong double resonance, it departs from it. And so actually, my original version of the proof, I thought this was all that you get something. Well, you get something of size square root of epsilon. I mean, the thickness of this is square root of epsilon. And then, using the minimizing principle, I wanted to go along here and like that. Well, using this step 2, which I haven't described at all. Once I get the locational Aubry sets, I should be able to do this. Actually, it turns out that even this wasn't true. Sometimes this pinches down to a point. That was my mistake. I failed to see that sometimes it pinches down to a point. That can happen at most finitely many points. It's the way it happens is that just to understand the location of the Aubry sets, you take an average system, and for most points you just average with respect to this one resonance. But in this line there's a dense set of points which has a second resonance. And now if the denominator for the second resonance is not too large, then you call that a strong second resonance. So there's a finite set of points which has a strong second resonance. And to understand the location of the Aubry sets when you have a strong second resonance, it depends on looking at an average system where you average over a circle. So the average system has the form of a has the form of it's a kinetic energy associated to a Riemannian metric on the 2 torus plus a potential. Well, I call the potential the negative of the potential energy. So excuse me for that. So you have this Lagrangian, this average Lagrangian of this form. And now, when you have an average Lagrangian of this form, there's something called a Jacobi metric. The idea is to find the Aubry sets for the average system, which are the same as the shortest curves in a certain homology class for the Jacobi metric. Well, for each energy level, E, you have a Jacobi metric for E greater than equal to E0. Unfortunately, the Jacobi metric at E0 degenerates. There's one point under my genericity hypothesis. There's one point where it degenerates. So you have a metric which is a nice smooth metric everywhere, except at one point where it becomes 0. And the shortest curve. Well, there's a very simple theorem in Riemannian geometry that, as far as I can see, it was first proved by Morse. That if you have a Riemannian metric and you take a shortest curve in a homology class, it's a simple curve. And my mistake was I thought this was also true for the degenerate case. But for the degenerate case, you can have the curve might have, the shortest curve in a homology class might be union of two curves, each one in a different homology class. And in that case, this thing actually pinches down, and for several weeks I was convinced my whole proof collapsed, but then when I realized that. But then I realized that I could make yet another construction where it pinches down. Well, let me blow this up. So you have this thing pinching down here, H. Now you have these two curves. Actually, you have a region like this, which is I can't explain I don't have time to explain what this is, but anyway, you have these two curves, and they have homology class H1, and they don't pinch down. So there's a construction which allows you to go from here to here, and then into here, and then through there. Okay, so this is a lot of hand waving, but that's the best I can do, I think.